In this lesson, we will discuss the concept of energy levels, focusing on the levels of the hydrogen atom. Through very complex calculations and experimentation involving quantum mechanics, one of the most important things we've come to understand about electrons is that they are only able to occupy very specific volumes of space around the nucleus of an atom, and these specific volumes depend on the electron's energy. Thus, the energy of an electron is also restricted to special quantities, meaning energy is quantized. Let's think of this in terms of a staircase. If an electron is at a certain step on a staircase, it requires a specific amount of energy to climb up to the next step, or energy level. It receives this energy from electromagnetic waves, like light waves. If it doesn't get exactly the right amount of energy, it's not able to move up. If, however, the electron is hit with a light wave with exactly the right amount of energy, electrons can move up even multiple steps. Similarly, electrons can go down a step or energy level, and in doing so will emit energy rather than absorbing it. The amount of energy the electron will emit, in the form of light waves, is exactly equal to the amount of energy required for it to jump up to that step in the first place. Now, the amount of energy required to go up a step, or energy level, is different for every step, so our staircase actually looks more like this. On top of this, the staircase is different for every atom. So the amount of energy required to move up or down energy levels depends on which atom we're looking at, as well as which specific energy levels we're looking at. We'll focus on the energy levels of hydrogen, as the hydrogen atom is the simplest of atoms and was used for most experimentation. Now, to discuss hydrogen's energy levels, we must first take a look at Bohr's model of a hydrogen atom. Bohr's model of the atom consisted of a positive proton in the nucleus with an electron moving around it in a circular orbit. He used the letter N to label the multiple orbits. Though we now know this model and way of thinking about electrons is incorrect, Bohr used this model to develop a formula for the energy of the electron, and it was in fact an accurate formula despite the inaccurate model. Bohr determined that the energy of the electron is equal to negative r subscript h over n squared. R subscript h is the Rydberg constant, which is equal to 2.179 times 10 to the negative 18 joules. N symbolizes the orbit number. Using Bohr's formula, the following energy level diagram for the hydrogen atom can be created. This tells us the amount of energy an electron in the hydrogen atom has from its first orbital to its fifth orbital. There's a couple things to take away from this diagram. Firstly, all the energies are negative because zero energy corresponds to a situation where the electron is infinitely far away from the nucleus. Since energy decreases the closer the electron gets to the nucleus, this means the energy for all other distances must be negative. Another important note is that as n gets larger, the difference in energy between levels decreases greatly. This means the amount of energy required for an electron to move from the fourth orbital or energy level to the fifth orbital is much less than the energy required to move from the ground state to the second orbital.